Now, this part is about air conditioning and its processes. Air conditioning and its processes. Now, these are the technical terms that we have to know when we do this particular section, air conditioning. The first thing is the relative humidity. Then you have specific humidity, dry bulb temperature, wet bulb temperature, dew and dew point temperature. So these are the things we will be concentrating on the first part of air conditioning. Now, we are not looking at the processes yet. Processes will be in part 2. So the objective of this section, one is to differentiate between dry air and atmospheric air. So when we go into the subject or when we go into this chapter, we will define what is dry air and atmospheric air later, afterward. Okay, and then define and calculate the specific and relative humidity of atmospheric air. Then calculate the dew point temperature of atmospheric air. Relate the adiabatic saturation temperature and the wet bulb temperatures of the atmospheric air. Now, everything will be explained afterward, will be defined and explained. And there will be examples showing you how to, find or how to determine all these temperatures and the humidities. Okay, use of psychrometric chart. The use of psychrometric chart, I will also be explaining or telling you how to use a psychrometric chart. Now, apply the principle of conservation of mass and energy in solving problems in air conditioning process, which will be in the next part. Okay, these are the objective of this chapter. Okay, so about air conditioning. Now, so I will just read out this because this is just an explanation why air conditioning system or process has came into the world. Okay. Now, today, modern air conditioning system can heat, cool, humidify. Humidify, that means adding water vapor or adding moisture content into the air, means humidify. Dehumidify means removing of moisture. Removing the moisture, so the air that is blown out from the air con will be drier. Here, it will be more wet or wetter. Here will be drier. Okay, clean and even deodorize the air in the other, the air. In other words, okay, condition the air to people's desires. Okay, now the rate of heat generation by human body depends on the level of activity. For an average adult male, it is about 87 watts when sleeping, 115 watts when resting or doing office work, 440 watts when doing heavy physical work. So these are the amount of heat that is released or generated by our human body. Now, when doing light work or walking slowly, about half of the rejected body heat is dissipated through the perspiration as latent heat, while the other half is dissipated through the convection and radiation to surroundings, with the surroundings, as sensible heat. Now, in an environment at 10 degrees C with 48 km/h winds, feel as cold as an environment of -7 with 3 km/h wind as a result of body chilling effect of the air motion. Now, the comfort of human body depends primarily on 3 factors. 1, the dry bulb temperature, which is the normal temperature, the normal temperature reading from the thermometer. Okay, so it is known as dry bulb temperature because the device that we use is called a dry bulb thermometer, which I will explain later. And then it depends also on the relative humidity, which is the amount of moisture in the air compares to 1 kg of dry motion. Motion also plays an important factor in human comfortability. Now, the relative humidity affects the amount of heat a body can dissipate through evaporation. So if the humidity is too high, the dissipation will be slow, will be lower. Now, if the humidity is too low, you find that the air is too dry. Okay, so most people prefer a relative humidity of between 40 to 60%. Now, air motion removes the warm, moist air that builds up around the body and replaces it with fresh air. Air motion should be strong enough to remove heat and moisture from the vicinity of the body, but gentle enough to be unnoticed. Okay, that is air motion. Now, important factor that affects human comfort is heat transfer by radiation between the body and the surrounding surfaces, such as the walls and the windows. So that is why, okay, so it's very important for us to look into the size of the room and the wall, whether it is insulated, and the window as well. Okay, so more windows, it is better or not, then we have to analyze later on. Now, other factors that affect comfort are air cleanliness, odor, and noise. Okay, so that is basically what is air conditioning. So here it simplifies and give you, okay, this section here telling you what is aircon. Human beings have an inherent weakness. They want to feel comfortable. They want to live in an environment that is neither hot nor cold, neither humid or dry. So that is why we call it as conditioning. So we are conditioning the air. Okay, so conditioning the air so that, okay, the air that is blown out from that device, okay, we feel comfortable. Okay, that is why it's called air condition. Now, however, comfort does not come easily, since desires of human body and the weather usually are not quite compatible, because sometimes it's too hot, sometimes it's too cold. Okay. The first term, what is dry air and what is atmospheric air? Dry air can be viewed as air, an amount of air which inside contains no moisture, no water particles inside, totally no water particles or moisture within the air, the sample of air which we have taken. So if there is totally no moisture, okay, then we call it, or we consider it as dry air. So usually atmospheric air consists of air by itself, dry air, we call it as dry air, and then moisture and other form of gases. Since we are doing air conditioning, we only concentrate on the air that is with dry air and moisture only for this section, for aircon. Okay, so those other gases we neglect. Okay, those we will take into account when we do combustion. That is a different chapter, different section. Okay, now atmospheric air in the atmosphere containing some water vapor. So atmospheric air is actually the mixture of air and water vapor. Now, in most of our studies, we assume that air remains constant. The flow of air remains constant. The only variable that changes depending on evaporation, perspiration, and all those things is the water vapor. So the amount of water vapor that is in the air can fluctuate. Sometimes it's higher, sometimes it's lower. It depends on the weather, the surroundings. Okay, whether it's hot, it's cold, or it's humid, or not so humid. Okay, if it is humid, that means the moisture content in the air should be very high. If it is less humid, that means the content of moisture in the air is less. Okay, so usually, let's say for example, you adjust or your air conditioning, the air that is coming out from your air conditioning is only 40% relative humidity. That means it has a very high chances of absorbing or taking all the water particles that is inside within the room. So if the humidity is 40%, so usually what happens is people who are sleeping in the room or sitting in the room while they are in the office, the amount of moisture removal from their body is very high. Is very high. Now dry air. Now air that contains no water vapor, air that contains no water vapor in the air, okay, is considered as dry air. Only the air by itself, so we call it as dry air. Now, water vapor in the air plays a major role in human comfort. Therefore, it is an important consideration in air conditioning applications. Now, water vapor in the air behaves as if it existed alone and obeys the ideal gas relationship of PV equals to RT. We call it as perfect gas because, okay, it doesn't undergo with whether it is in the form of solid, liquid, or vapor. It doesn't go under any chemical reactions when you mix them together. So we can sometimes, or most of the time, we can call them as perfect gas. And we assume that at low temperature and low pressure, they actually follow the ideal gas law of PV equals to RT. And remember how to calculate the specific gas constant or the characteristic gas constant is by taking the universal gas constant of 8.3144 divided by its molecular weight. Let's say, for example, water H2O is 18. So if you take 8.3143 divided by 18, you will roughly get 0.4619 kilojoules per kg. Okay, which is different from the A. A is 0.2871 for standard, okay, characteristic gas constant. Now, the atmospheric air can be treated as an ideal gas mixture. So it is a mixture of dry air and moisture. Now, so based on Dalton's law, okay, we have total pressure, that means the surrounding pressure, the total pressure is actually the sum of pressure, the partial pressure of air and the partial pressure of water vapor. So PA here stands for partial, P-A-R-T-I-A-L. Partial is air and partial is for water vapor. So when you add them up, okay, you get what we call the total pressure of the surroundings or the atmospheric pressure. Sometimes we can call it as the atmospheric pressure if this is atmospheric air. So PA is called the partial pressure of dry air. And PV is called the partial pressure of vapor or the vapor pressure. Okay? Now, that is the specific and relative humidity. Okay, so specific humidity is actually the ratio, humidity ratio, that is taking the mass of water vapor that is present in the air, the mass of water vapor that is present, or moisture that is present in the air, okay, to the unit mass of dry air, that means per 1 kg of dry air. So you can have m dot v or mv over ma. Okay, m with the subscript v or m with the subscript a for the dry air, m with the subscript v for the moisture. So the specific humidity is actually the ratio between the mv and the ma. So you can take specific humidity, the symbol that we use here is omega, and it's the ratio of the mass of moisture per kg of dry air. So in the simplest form, it can be defined as mv over ma. Or it can be equals to 0.622 PV over P minus PV. P is the partial pressure of water vapor. PV is the partial pressure of water vapor when the A is unsaturated. When the A is unsaturated. So the next thing is we go to saturated and unsaturated A. What does that mean? Okay, so this formula is applied to find the specific humidity, and this formula can be proven. Okay. Now, saturated A. The next thing is saturated A. What is saturated A? A that contains the maximum amount of water vapor that is possible at a given temperature and pressure. Example, A in which the relative humidity is 100% is called saturated A. So if the relative humidity is 1 or 100%, that means we can say the A cannot accommodate any more water particles. The A cannot accommodate any more water particles. So as A, dry A, let's say dry A or A, normal A, yeah, blow or flow across a stream of water or a pond of water, or it flows across our wet body. What happens is it will pick up water particles from the surroundings. It will pick up water particles from the surroundings until it is full, until it cannot take in any more water particles. So at that stage, we called it as the saturated A. The saturated A. Now, unsaturated A is when the A does not contain. That means unsaturated A means the A is still able to take in water particles. Take in water particles. It's just like a sponge. Okay, when you used to wash your dishes or you used to wash your plate, your cups, that sponge. Okay, if let's say for example you press until each single droplet of water out from the sponge, then we say we can consider that as dry A. So there is no more water inside. That is unsaturated, or that is called dry A. But then when you start dipping the sponge into the water, what happens is it will start to take in water particles, or it will start to take in water. So what happens until the stage when you lift up the sponge, you can see water start to drop out. That is the condition, that is the situation when the A has become saturated. So unsaturated, that means it is still able to absorb, or it is still able to take in water particles. It's called unsaturated A. So that gives you the difference between saturated and unsaturated A. Okay. So this term here, okay, this term here, phi, is called the relative humidity. This is called the specific humidity. This one is called the specific humidity. And this is called the relative humidity. Specific humidity is a ratio of the mass of water vapor to the mass of dry A. Usually it refers to 1 kg of dry A. But then when you refers to the relative humidity, that means this phi here, is mv over mg. And what is this mv and what is this mg? mv is actually the mass of water vapor. mv is the mass of water vapor when the A is unsaturated. When the A is unsaturated, mv is the mass of water vapor when the A is still not saturated. mg is the mass of water vapor when the A has become saturated. And simplifying this ideal gas for mv and ideal gas law for the mg, you've got PV over PG. Now, what is PV and what is PG? PV is the partial pressure of water vapor when the A is not saturated. PG is the partial pressure of water vapor. PG is the partial pressure of water vapor when the A has become saturated. I repeat, PV is the partial pressure of water vapor when the A is not saturated. PG is the partial pressure of water vapor when it is saturated. So actually both of them are referred as partial pressure of water vapor. PV and PG are both referred to be partial pressure of water vapor, where V refers to unsaturated A, G refers to when the A has become saturated. So PG usually refers to the saturated pressure at that particular temperature. That means if let's say today is 32 degrees C, so you will have a partial pressure of something. Okay, you have a saturated pressure, which I will show you by referring to the table afterward. So this is relative humidity. That is the ratio of the amount of moisture. That is the ratio of the amount of moisture that the air can hold. Not saturated, yeah? That is MV. To the maximum amount of moisture. Actually, both are referring to moisture. Okay, the air can hold. That means it's to the maximum when the air has become saturated. Okay, so that will give you the relative humidity. It can also be defined further as moisture content over moisture capacity. Remember, moisture content over moisture capacity, the relative humidity. So these are the technical terms, the terms that we use in air conditioning. So if let's say we want to find relative humidity, we can use this formula here. We can also use this formula. We can use this formula, okay? This one is when you can see there is no PV inside the formula. So actually you can manipulate these two formula, you get something like this, okay? So you can use this formula to find out your relative humidity, or you can use this to find out your specific humidity without the PV, or in terms of PG and the total pressure. This is total pressure, yeah? Total pressure. This is partial pressure of water vapor when the air has become saturated. This phi here is the relative humidity. This omega is the specific humidity. Now, what is this 0.622? So if you take RA over RV, RA is 0.2971. If you take 0.2971 divided by 0.4619, if you have a calculator, you can calculate. If you take point, hold on, 0.2871 divided by 0.4619, okay? So you will get a value of roughly around 0.622 if you use your calculator to calculate. RA is specific gas constant. The characteristic gas constant for ARA is standard as 0.2871 divided by RV, okay, which is the characteristic gas constant for H2O, which is 0.4619. Okay, you will get a value of roughly approximately 0.622 or 0.623. So now here I'm going to show you an example. Let's say the air in our surrounding today air temperature is 25. And this temperature, usually we call it as the dry bulb temperature, DBT. That means the normal temperature. So let's say the normal temperature today, okay, the weather today has a temperature of 25 at this moment. So because you have to refer to that instant, okay, because temperature fluctuates sometimes, yeah, because especially due to now the weather changes globally, okay, so we hope the temperature doesn't fluctuate like that. Okay, so we take it as this pressure, the atmospheric pressure, and with this temperature. Okay, so what happened is when you look at this temperature from your property table, you get your saturation pressure is 3.1698 kPa. This is when the air is saturated. So that means this will be your PG. This will be your PG. So when you look at this table here, I got this table here done for you. So let us take a look at 25 degrees C. That means here, 25 degrees C. You can see the pressure here. This is the saturation pressure at this temperature, which is 3.1698 here. okay, at 25. So this is the temperature, or we can call this as the dry bulb temperature, normal temperature. Okay, so the saturation pressure is 3.1698. That should be your PG. So this would be your partial pressure of water vapor. This would be your partial pressure of water vapor when the air is saturated. When the air is saturated. So that is why it's the PG. Okay. So now, if PV is the partial pressure of water vapor when the air is not saturated. When the air has not been saturated yet, that means when the air is about to start to take in water particles. Okay, but then not full yet. So that would be PV. So for dry air, PV will be 0 because it's totally no moisture inside. There is totally no moisture, no water content inside. So that is why the PV is 0. Now PV always less than 3.1698 kPa when the air is not saturated. When the air is not saturated, it's always less than this pressure at this temperature. Okay? Then when PV is equals to, when PV reaches at 25 degrees C, when PV reaches to this pressure, that means the air has become saturated, and this will change to PG. This will change to PG. When PV approaches 3.1698, that is for saturated air. This PV would be equals to PG. So if, let's say, for example, I give you 30 degrees C. 30 degrees C, the partial pressure, sorry, the saturated pressure is 4.2469. Oh, sorry, 4.2469 kPa. So that would be the partial pressure of water vapor when the air is saturated. So now if, let's say, for example, you examine and you got a pressure which is less than 4.2469, that means that would be your PV. If, let's say, it approaches 4.2469, okay, then the air is already saturated. I hope you all understand what I've explained, yeah, based on 25 just now. Okay, so based on different temperature here, is, let's say, for example, if today is 30, then the saturation pressure will be this. So for the air becomes saturated, the pressure must reach this value. For the air becomes saturated, it means full of moisture, it must reach this value. If, let's say, you are referring to 35, usually I think these few days are 35 degrees C. So the partial pressure of water vapor is 5.6291. So that means when PV approaches this, that means the air has become saturated. If PV is still less than this value, the PV, that means the partial pressure of water vapor, when the air is not saturated, that is considered as PV, partial pressure of water vapor. So it is below this value at 35, then we say the air is not saturated. Now, if PV reaches this value, it won't go above this value. If PV reaches this value, that means the air has become saturated. Okay, I hope you understand what I've explained. So remember, what is PV? Partial pressure of water vapor for unsaturated air. PV, which is equals to PG, approaches PG. Partial pressure of water vapor, and it is already saturated. The air already saturated. Now, in most practical applications, the amount of dry air in the air-water vapor mixture remain constant. Remember, mass of air here. That is what it is explained here. This amount here is always constant, remains constant, unless you are referring to mixture, adiabatic mixing process, where you mix air from two different streams. Then the amount of air will not be a constant. But then if you are referring to a single stream, single line of air, that means the mass of air is constant. But then unless you are referring to 2, 3, 4, 5 stream mixed together become one stream. So each of the stream will have a different amount of air. Okay, but then if you are referring to one single stream, then that amount of air is constant. Okay, but then the water vapor, amount of water vapor always changes. Now the next thing is the enthalpy. Enthalpy play a very important role here in order to measure how much of power, how much of heat. Okay, so Enthalpy of atmospheric air usually is considered as the mixture. It's also mixture. So the enthalpy of mixture, this is the enthalpy of mixture, which is considered consists of HA, that is for dry air. Remember, this is A, subscript A, that means dry air. This is subscript V, that means water vapor. So we start off with absolute enthalpy. So by energy balance, this can also be referred to energy balance. So the total enthalpy or the enthalpy of mixture actually consists of the enthalpy of dry air plus the enthalpy of water vapor. So then we can also say is that this absolute enthalpy here is actually the product of mass and specific enthalpy. Mass and specific enthalpy with respect to air and with respect to water vapor. Okay, so if let's say, for example, we start dividing throughout the whole equation by MA. Okay, so dividing throughout by MA. So if you take this H divided by MA, it will actually give you the specific enthalpy of the mixture. Specific enthalpy of the mixture, because this is always a constant. Okay, so it gives you enthalpy, specific enthalpy H. So when this H divided by MA, you get the specific enthalpy of mixture. This divided by MA, so you see. And this divided by MA actually becomes your specific humidity. Remember, the specific humidity actually is the ratio of the mass of water vapor to the 1 kg of dry air. So this becomes 1 and this becomes omega. So this will be the enthalpy of mixture. This will be the formula that we use in order to calculate the enthalpy of atmospheric air or air. So HA can be found by using CPT. HA can be found using CPT, where CP for A is standard based on 1.004 to around 1.006. But we consider it as a constant at low temperature, which is CPA is 1.005 standard, multiplied by the temperature of the air, usually is the dry bulb temperature dBT. Then omega HV. HV can be found by taking the Hg at that particular temperature. HV here can be taken or can be found by considering the Hg at that temperature. Okay, which I will show you how to do it afterward. Okay, so you will have H equals to HA plus omega Hg. Hg here refers to the saturation temperature. That means if let's say 25 degrees C, okay, the air temperature is 25 degrees C, then you have to refer to Hg at that temperature. Then HA, you can take CPA 1.005 times 25. Okay. Now, so why we say that? So that when you look at this at low temperature here, you can see a CPA here is almost constant, 1.005, almost constant. So if you average it out, it will come to a value of roughly around 1.005 with an error of around 0.2%, under 0.2%. Okay, CPA can be considered as 1.005 kilojoules per kg K, Kelvin missing here. Okay, there is a Kelvin or a degree C, which is considered as a constant. Or you can use this to find out the specific volume of mixture also. Can use this by finding out the volume of mixture by taking VA and omega VG, specific volume, okay? So VA and VG can be found by applying your ideal gas PV equals to RT or PV equals to MRT. Usually you use PV equals to MRT because you are considering the mass of air on the mass of and the mass of water vapor. Okay, so to find VA, we can use this PV equals to RT or PV equals to MRT, the best. Okay, or if you want to find VG, you can use PG, VG equals to RG, TG. RG is 0.4619. Okay. So that's for the enthalpy and the specific volume. So what is dew point temperature? First one is the dew point temperature. So now we are looking into the 3 different temperatures. One is dew point, second is the dry bulb, the third one is the wet bulb. So the first one is the dew point temperature, the temperature at which condensation begins. So if let's say, for example, you have a stream of cold air which flow across a can of Coke, which you have just taken out from your refrigerator. So as the air, the humid air flows across the bottle of Coke, what happens is it will leave or stay or mix, sorry, I use the word leave, leave a certain amount of water droplets on the surface of the can, which we call them as dew. So the temperature at which these dew are formed is called dew point temperature. Okay, the temperature at which condensation begins. So as the cold air, saturated air, just touches the cold can, what happens is the moisture that is in the air, which is the moist air, will start to be squeezed, will be squeezed out from the bulk of air and then left behind on the surface of the can, okay, as dew or droplets of water, okay, or we can sometimes call them as condensate. Now, the saturation temperature of water corresponding to the vapor pressure. Remember, for moist air, when it comes into contact with any cold surfaces, it will leave or it will left some water particles on the surface of the object, okay, of the cold object. So let's say, for example, you have a piece of leaf. You can see these droplets of water here. We call them as dew, D-E-W, okay? So liquid water or droplets here, which we call dew. But the surrounding air, the air which is surrounding these plants must be, let's say, for example, moist air, especially at night after rainy season. After rainy season, especially at night, what happens is you can see some of the grasses or our plants, okay, or grasses that cover off with droplets of water like that. This is called dew, okay? So the temperature at which these are formed are called the dew point temperature. The surrounding must be of moist air. So when it touches the cold surface, it will leave behind all these droplets of water. Now, when the temperature of the leaf is below the dew point temperature of the surrounding air, it sweats. Okay, if this surface here, this cold surface here, the temperature of this cold surface here is at a temperature lower than the dew point temperature, it will leave these droplets of water on the surface of any on your windscreen, or let's say, for example, you take a bottle of cold water out from the refrigerator, or you take away a packet of cold water. After a few steps, when you walk, you can feel that, or not after a few steps, a few seconds later, you can see that outside of the bag is filled up with droplets of water. That means the surrounding air, if let's say, is moist, okay, saturated. So when it touches any cold surface, it always will leave behind all these things here, which we call dew. So TDP is actually the dew point temperature, which is also the saturation temperature at the PV pressure. Okay. So PV here is constant pressure. So what happens is at constant pressure, when the temperature drop, okay, especially when the flow of air across this colder surface here. So what happens is at the surrounding pressure, which is constant. So what happens is the temperature will drop until it reaches this dry saturated vapor line here. So any further heat removal, this is called dry saturated vapor line. Any further heat removal, it will causes it to move inside the dome. That is wet vapor, which is the mixture of vapor and dry vapor and liquid, or we call it as wet vapor. So you have condensate, or you have water being pressed out from the air, squeezed out from the air, which we call them as dew formation. Constant pressure cooling of moist air. Remember, surrounding pressure, atmospheric pressure. Now, our surrounding pressure is 1.01325 if let's say on the ground level. Now, in cold weather condensation, here I give you one example, okay, which I have taken out from the book. Now, in cold weather, condensation frequently occurs on the inner surfaces of the windows due to the lower air temperatures near the window surface. That contains A at 20, this is your DBT, dry bulb temperature, and 75% relative humidity. At what temperature will in the air start to condense on the inner surfaces of the window? Here, got a diagram. Here, you got a window, okay, which is at 16 degrees C. So outside, you have the surrounding air. So from here, we are looking at the dry bulb temperature, the DBT of 20, okay, contains A of 20, yeah. So 20, the saturation pressure is 2.3392. So the dew point temperature is actually the saturation temperature at the pressure. So one is now relative humidity is equals to PV over PG. I've given you a formula before this, remember? Okay, so this PG should be based on the DBT of 20 degrees C, which is 2.3392. And the relative humidity they have given us 75%. So when you take this multiplied by this changing PV to be the subject, you will get a PV of 1.754 kPa, which is less than this value. Okay, so that is why we say this is the partial pressure of water vapor when it is not saturated. So then based on 15 degrees C or based on this pressure 1.754. So 1.754 is in between these two values, 1.7057 and 2.3392. So what we have to do is we have to do interpolation. So by interpolation, you can see we don't know the temperature in between based on this pressure. So 15, 20. We got this 1.7057 and this as 2.3392. So we want to measure the dew point temperature based on this pressure. So what we can do is we can do interpolation here to find out the dew point temperature, which is the saturation temperature at this pressure, at the PV pressure. So we can do interpolation and find out the dew point temperature, which is 15.4. Okay, this is one example. Okay, how you can find out the dew